So we were taking the papaya example to give an intuition to the kind of things that we are going to do. So let me redefine our current formal model and how it relates to the papaya example. So we talk about a formal model of learning, and we are motivated by the papaya example. So what does the model contain? So we have a formal model for learning. So the first thing that we need is some domain set. The domain set is the domain over which the instances are coming from. So we have a domain set X, and if we go to the analogy of the papaya, this is what is the domain set in the case of the papayas? What is our domain set? Yes? What do you say? Right. So the domain set in the case of papayas is our set 0, 1, square. Note that if we formally want to learn about the papayas, we don't take papayas as our input, but we take the features of the papaya of the input. So my domain set is not fruit, but my domain set are pairs of values, the color and the softness of the fruit. Okay? So we have our domain set. Then we have the label set. Y, which in the case of the papayas, the label set is just going to be tasty, not tasty. Then we have the kind of data that we get for training. So we have a training input to the learner, which is a training sample. And we usually denote it by S. And we assume that this training sample in this scenario of learning to classify, it consists of points x1, y1 up to xm, ym, which is in the case of the papayas is just a set of already tasted papayas. Okay. Now the next element that we need is what is so this is the input to the learner. That's what the learner is playing over, and that's the input to the learner. So the next component that we need is what is the output to the learner. The output of the learner. So the next element is the learner's output, and what we want the learner to output is a predictor or a predicting function. So we want the learner to output some function, let's call it h, a hypothesis, that goes from our domain to the labels. So the learner outputs a function, it takes this sample as input, outputs a function, that this function attempts to be able to predict the label of every new point. Right? So in the case of the papayas, it's going to be just a predicting prediction rule for tastiness. Now, the next thing that we need is to somehow define how well are we doing. So we want a notion of the quality of such an H. So the next thing I want to define is the quality of such an H. And for that, I make my first assumption. So we assume that the data there is some distribution that generates the papaya. So the quality of such H is determined with respect to some data generating distribution and labeling rule. So okay, so now we assume that the data is generated, the papayas are generated by some distribution over papayas, and there is some rule that determines, given the color and softness of a papaya, the rule determines whether the papaya is tasty or not. So we call it L of D of F. So L stands for loss. D is the distribution that generates papaya in the world. And F is the function that determines the tastiness of the papaya. And now we want to define LD of some hypothesis H. And it is just going to be the probability that our H fails. So it's going to be the probability, our probability distribution is D. So it's going to be D of the set of all x's such that H of x is not equal F of x. Okay, so this is maybe the first, a little bit more complex notion. So we assume that there is some distribution that generates papaya, and we want to know, we have some kind of prediction rule. We want to know how good it is. Now, what we care about is how well my rule will behave in reality. So if it fails on some very unlikely instances, I don't really care. What I really care is what is the probability under the way the data is distributed, is generated. What is the probability that my predictor that I'll get the papaya such that my prediction rule will not agree with the true tastiness of the papaya. I'll make an error. So this is kind of the probability of error. Any questions at this point? It should make sense to you. If not, just ask. So I have a prediction rule. I don't count how many times it's going to err because I don't know what is my universe of all papayas. It could be infinite. But what I care about is the probability that I will encounter an error. Yes?
The DF subscript, that's a distribution function?
So D is the distribution that generates papaya. And F is a rule. F is the true labeling, is the true function that takes points of x and give them some y. So you have the correct labeling. This is the correct labeling function. We would have liked to find the correct labeling function. That would have been perfect. But we don't know it. All that we will see is just a sample. So instead of finding the correct F, we find some hypothesis H. And now how good is this H? H is as good as its agreement, the probability that it will agree with the correct F. Yes?
Are we being permitted?
He was asking first. Yeah.
If we assume the existence of such an F, doesn't that force us to accept that tastiness is solely a function of?
Right. That's a very good point. Assuming the existence of such an F is already a non-trivial assumption. It is assuming that really the taste of the papaya, because remember, X is not fruit. X are 2 points or 2 real numbers, taste and color. Not taste. Softness and color, right? So assuming such an f is making the very strong assumption that tastiness is fully determined by the softness and color. And this is a strong assumption, and we will relax this assumption in 20 minutes. That's a very strong assumption. But the funny thing is that when machine learning started in 84 with this paper that I already mentioned of Les Valiant, it went for about 10 years before people attacked this assumption. So you should have come there in 84. How old were you then? Very young. -9, okay. And made this comment then. Yes? Same question, okay. So that's a strong assumption, and we will relax it later. So we assume that, so this is our notion of error, where I use the letter L to say loss. So the goal of the learner, so these are the rules of our game so far. So now we determined our game. What is the goal of the learner is given S to come up with H of small loss. Right? That's the loss of H. That's what the learner is trying to do. So what is a reasonable strategy for the learner? You see a sample. You see the labels of the sample. What is a reasonable strategy for the learner? So here is a very sensible strategy and a very basic learner strategy. And it's called empirical risk minimization. Or in short, ERM. And the idea is to say, I don't know anything about f, and I don't know anything about distribution. All I know is the sample. So let me try to find a hypothesis that works well on the sample. Because all I know is the sample. So I'll try to find something that works well in the sample and hope that if it works well on the papayas that I've seen so far, it will also work well for papayas that I will see in the future. Okay? So let us define it more precisely. So we define the loss of H with respect to the sample. You remember, the sample is a sequence of points and their labels. So given a sample, we define the loss of S with respect to the sample. See, this was the loss of F of H with respect to the true data. But this is the loss of H with respect to what we have seen. Some kind is also called the empirical loss of H. And how will it be defined? It will just be defined as the fraction of points on which our H errs. So it's going to be the size of the set of all I such that H of xi is not equal yi divided by the size of S. So we have our prediction rule H. H take x's as input and outputs a label. But on my training sample there, I had x's with their labels. So I can look at my H and ask how often did it disagree with the labels on the sample. And this fraction is my relative success on the sample. That's what I can actually measure from what I see. Question now? Yes?
If you can pick age sort of freely, why would you make this ever more than 0?
What do you say?
If you can pick H, if the learner is trying to pick H, why would this be more than 0?
Why would this be more than 0? You're running a little bit ahead of me, but only 5 minutes ahead of me, which is good. I will catch up with you soon. Yeah, it's a good question. But what he's saying, if I repeat what he's asking, why not always pick an H so that this will be 0? Right? And that's what I want to address. So why not always pick an H that makes 0 error here? So how can I pick an H that will make there 0 error? I will just, here is a simple rule. So a very simple rule for finding H with small empirical risk. What will I do? I will define H of S. H depends on H. I'll define H of S. I will define it as. Now, I have to tell you how my hypothesis is going to behave on every x. OK? So I get some x, and I have to tell you how to behave. So I will define H of x to be as follows. It will be if x equals xi for some xi yi in my sample, what label will you predict? If you see a point that is already there in the sample, what label will you predict? Yes? Yi. Otherwise, predict, say, not tasty. So this is a very nice rule. What is the error of this guy on the sample? On the sample, it makes 0 error. On the sample, it makes 0 error. So ERM, the LS of my HS that I just defined, is 0. OK, so just make sure that you all see why this is the case. Yes? What do you say? Right, so why aren't there any contradicting elements of the sample? That's a very good question. And the reason is that we assume that there is some function according to which the sample is labeled. Later, when we will relax this assumption, it may be the case indeed that there are some contradicting elements of the sample. There could be in the sample 2 papayas that have the same softness and same color, but one of them was tasty and one of them was not. But for now, we assume that this is not the case. That is a deterministic function that determines in a non-ambiguous way, determines the sample. So the loss of this will be, so now, but is it a good hypothesis? What is the probability of success of this? We want to minimize the probability of error on the true data. Now we came up with this guy. Is it a good predictor? Is it going to have a low probability of error? Yes?
It depends on the distribution.
It depends on distribution, but can you guarantee that it will have low error?
Oh, no.
Of course not, right? It could be that all the papayas are tasty. All the papayas in the world are tasty. I mean, it's not a matter of the papayas. It's a matter of how hungry I am. So everything looks tasty to me. And I'm using this rule. And in this rule, I will just eat, some papayas that I bought for sample. But from that point onward, I will never buy another papaya. I'll just starve to death. Because any papaya that will not be exactly like the one that I have already tasted, I will predict that it's not good. So it's not a good rule. So we really have to amend this empirical risk minimization technique. It looks like the only thing we can do is empirical risk minimization, because all I see is my empirical data, my sample. I don't know anything else. What better can I do? But it's not a good solution. OK, so first comment is that this scenario in which you have a hypothesis that looks let's have a very small error on the sample, but still a bad error in reality. It's a very important phenomena to watch out from, and it's called overfitting. And overfitting is a real problematic rule in reality. That something behaves very well on the sample just by chance, but in reality it may behave very badly. And overfitting is something that people tend to do in real life all the time. I don't know. My prime example was from the last election in the US. So in the election of the US, they say that I think Ohio is a very, I don't remember if it's Ohio or which one is it. It's a very important state. It's very important to win Ohio. Why is it very important? Because in the past 20 years, the winner in Ohio was always the winner over all of the elections. It looks very impressive, therefore you should win Ohio, right? But the point is that if you think of it, that you have 50 states, and assume that each state is just tossing a coin. And you try to and in the past 20 years, there were only 5 elections. So you ask yourself, what is the chance that if I have 50 states, each of them tossing a coin, and there are 5 elections, what is the probability that one of them will hit the correct outcome all 5 times? And if you do this calculation, it's not so much. I mean, there's a probability of about 30% that you will have such a state that managed to hit correctly all the 5 previous elections. And then you take this state and you say, oh, it has wonderful empirical loss, 0 empirical loss. It predicted correctly all the elections so far. So maybe it also have a true loss, which is very small. It is very good in predicting the future. Let's try to win Ohio. But that's exactly overfitting. So maybe the first lesson from this class, and we will pump it in more and more and more, hammer it in, is that we have to protect against overfitting. Okay, so how do we protect against overfitting? That goes back to the, and we can go back to the examples of the pigeons. I mean, the pigeon that were pecking at some specific toy, it was pecking at the toy over all the time, and grains were coming. So it had some kind of an overfitting conclusion that pecking this toy causes the grains to fall from the sky. And that's kind of only correct by chance. So we want to fix the overfitting, so we take a precautionary measure. Now, if we go back to the examples of the rats and pigeons from last lecture, we can also guess what element is missing here. The missing element is some kind of prior knowledge. Without prior knowledge, we cannot learn. That was the big advantage of the rats. They had prior knowledge that poisoning is related to taste and smell of the food. And using that prior knowledge, they could be so successful. So we somehow have to introduce, we need to introduce to guard against overfitting, we introduce some prior knowledge or in other words, sometimes it's called inductive bias. Inductive bias because we are doing induction. We mentioned it last time. We are going to learn from some cases to make induction on other cases. We're doing induction and we have to introduce a bias. Without a bias, we will not be able to learn. So what is going to be our inductive bias? Assume that I know, now I introduce some prior knowledge. assume that I know that a correct labeling for my papayas come from some finite class. So for example, let us assume if this is my space of softness, or I don't remember which was which, color and softness, let us assume that we know that good tasting papayas live in some rectangle. And let us further assume that the number of potential rectangles is finite. But let's just make this assumption first. So we assume the prior knowledge that there exists a good prediction rule that is some axis aligned rectangle. We don't know which. We want to learn which one. But our prior knowledge is that there is some boundary of taste, of color, and some boundary of softness, such that if you live within these boundaries, you're going to be tasty. And now our goal, the goal of the learner, is easier. He wants to learn which is the correct rectangle, but he's not completely at lost. So now we will amend our empirical risk minimizer learner. So let H denote a fixed collection of potential or candidate prediction rules. In other words, every element of H is a prediction rule. It's a collection of prediction rules. In the papaya example, it could be the collection of all possible axis-aligned rectangles. So formally, H is a subset of the set of all functions that go from x to y. Instead of considering all possible prediction rules, I will also only consider a restricted set of prediction rules, this H. And we call it a hypothesis class, H. It's the class from which my hypothesis is going to come. And now we have a new version of the empirical risk minimization. So we have a new revised learning rule that we call ERM H. And ERM H, rather than trying to minimize the empirical loss over all possible predictors, is trying to find a predictor in H with a minimum empirical loss. So ERM H is the rule that say pick H in H that minimizes LS of H. But you're only allowed to pick in H. Or formally, I can write it as, I'll answer the question just in a second. So ERM H of some sample S is going to be a hypothesis that belongs to arg mean over all H in H of LS of H. So I will explain this notation, and you had a question?
Yeah, for the hypothesis class definition, what do you mean by the colon?
Okay. This is, right, I'm going to use a lot of this kind of simple set theoretic notation. This is the collection of all functions such that f goes from x to y. And sometimes we also denote it by x to the power y. All the functions that go from y to x. That's a common mathematical notation. All the functions that go from a set A to a set B, you denote them by a to the power b. But to save you this notation, I was trying to use this notation in the hope that it's more clear. But OK, it's a set of all functions that go from x to y. And H is just a subset of this. So that's one thing I wanted to explain. The other thing I want to explain is this. I don't know how many of you have seen this argmin. Argmin notation means it is a member of the set of all H's that minimizes this quantity. There may be more than one H that minimizes this quantity. What I'm saying here, I'm picking one of them. So I belong to this set. This is the set of all H's that have the minimum loss. So my ERM, my algorithm, my learner, will pick one of them, one of those with a minimum loss. And now, of course, it's not necessary that one of them will have loss 0, but we will see. So our next step is going to show that this ERMH turns out to be a good strategy. So by just adding this small correction, we add our restriction that rather than picking from the whole universe of functions, we pick a function from H. In many cases, it will solve the problem. So what we are going to show next is under some assumptions, we can guarantee that this is a successful learning rule, that it really leads to small error on the small error with respect to the true data distribution. So this is going to be our first theorem for the course. So we have here our first theorem. And the theorem is set in the framework that we just described. So I will not repeat what are x and y and so on. So I will repeat. Let x be any set. I don't care even it's finite, infinite. And y, let's for simplicity assume that y is just two values, 0, 1. And let h be a finite set of functions from x to y, to our 0, 1. OK? And now we make some assumptions about the data. So now we make a couple of assumptions. Assume the following. One, that the training sample S is generated by some probability distribution d over x, and labeled by some f in h. So you see here we are making a new strong assumption that the labeling belongs to the class H. We have a finite class H, a set of all, say, rectangles with some discrete coordinates, and we assume that the labeling is a function from this class. So we make this assumption, and we further assume, and the elements of S are picked IID. So according to P. So everybody knows what is IID, or some people don't. So IID stands for identically independent, what is it? Distributed. So this is identically independent distributed, but what it means is that every xi is picked independently of the others. Each time I pick a papaya, I don't do it based on how I picked earlier papayas. Any one is a new one, and identically means they are all picked by the same distribution, by the same distribution D. So we assume that our sample is coming by this type of random, memoryless process, that each time picks one sample, irregardless of what happened before. So that's the IID assumption. Then ERM H is guaranteed to come up with an H that has small true loss given sufficiently large sample S. So I'm not completely precise here. I don't want to state the exact parameters now. We will prove it, and we will see what parameters come out of the theorem. But what I care about here is the message of this theorem. The message of this theorem says that assume that the data is generated by some function in your H. Then you do your strategy ERMH. You have a guarantee that if you see enough samples, you will get a successful learning rule. You have to know that in our example of the ERMH that we had, the ERM that we had before without an H, it doesn't matter how much sample of papayas I see, I will always have a very big probability of error on future papayas, because I had a very bad rule. And here we say that once we restrict our attention to a finite class of potential hypotheses, we have a success guarantee. Now, before I prove this theorem, I want to comment on something that is here kind of going against or different than what you see in usual statistics. Usually in statistics, they tell you that you have to come up with your hypothesis before you see the data. I don't know how many of you have taken some basic course in statistics. You have some hypothesis H, you want to test it. You talk about hypothesis testing. Don't confuse it with papaya tasting. So what do you do in hypothesis testing? You say a doctor comes up with some assumption. He said, based on my experience, I think that people that smoke tend to have cancer. So he goes to the statistician with this hypothesis. Now the statistician wants to test this hypothesis, so he takes a fresh sample of patients, not the patients that the doctor has seen in the past. You take a fresh sample, which is independent of the hypothesis, and test the hypothesis on this sample. So it's a very basic rule, like a thumb rule that they tell you over and over in statistics. If you want to test the hypothesis, you need to use data which is independent of the hypothesis. The hypothesis should come first, and then I will test it on fresh data, right? But here, what we are doing is we are exactly trying to break this rule. We say we will come up with our H after we saw the data. You see, so, and this is something that goes against our basic understanding of statistics. I will pick my hypothesis after I see the data. So I can look at this class and come to the conclusion that women are more likely to wear glasses, women are more likely to wear glasses than men. And I test it on this class, and I see I have here 3 women in glasses, or 4 with glasses out of 6 women, and I have 4 men in glasses out of 40 men. So definitely women are more likely to wear glasses than men. What's wrong with this kind of reasoning is that I came up with my hypothesis based on the same data that I tested on. So statisticians will tell you this is a no-no. You have to come up with your hypothesis before you see the data. But what we are doing here is we're exactly doing that. We are picking H based on the sample. We say, what is ERMH? The ERMH says, look at your sample and pick a hypothesis that behaves nice on your sample. It's exactly what the statistician will tell you don't do. And that is something, why are we allowed to do it? We are allowed to do it because we restricted ourselves to this finite H. Why is it important that we do it? It's important that we do it because this is what learning is about. Learning, as opposed to hypothesis testing, is about developing theories based on the data, not about coming up with some theory before you see data. So it's a very important twist here. We are choosing H after we've seen the data. But what we did have in front of us before we saw the data is the collection capital H. And this is, of course, a strong assumption, but we will relax it. OK? So now I want to prove the theorem, unless there are any questions here. Yes?
What's the first word on the last line?
Here? Oh, it's distribution D over X. It's a distribution D over the set X. OK? OK, so we want to prove the theorem, although I did not phrase the theorem in very quantitative way. We will get the parameters from the proof. OK, so what is my proof? The first thing I want to consider is what are bad hypotheses. So I know that my algorithm is using ERM H, and I want to say when will my sample get confused? My sample will get confused if my learner will get confused if he sees a sample which is not representative. Like, this is how I got confused with my hypothesis about women more likely to wear glasses than men. I saw a sample which was not representative of the whole universe. So what are bad samples? So the set of confusing samples are those on which ERM H may come up with a bad h. So in order to quantify it, let us fix. So assume, let us fix some parameter, success parameter. Epsilon, some small number. So I will say that S is bad if it belongs to the set of bad or confusing S's is the set of all S such that my algorithm, my learner, so how do I denote my, okay, so that the true error of h of s, so h of s is the hypothesis that my learner comes up with when he sees s. The true error is greater than epsilon. So those are the bad samples. The bad samples are the samples for which I'm coming up with a hypothesis h that depends on s, and this hypothesis has error bigger than epsilon. Okay? And what we really care about is, I mean, we have here a way of generating S. The way of generating S is picking points independently at random. So we want to show that the probability that we will pick a bad S is very small. So what we want to estimate, we wish to upper bound the probability of getting such a bad sample. So let me denote this with a little bit more formal notation. So that my probability distribution is D, and I pick, say m is the size of my sample, so I pick points one after one after one m times. So my probability distribution is now m copies of D. It's the first copy of D to pick the first point, the second copy of D to pick the second point. I picked m points in my sample. So my probability is over m tuples. So I denote it by D to the m of the set of all S, of the set of all S restricted to X, such that the loss of the resulting hypothesis is greater than epsilon. Okay, I'm aware that with every step I'm introducing more notation which could be more confusing. So let me again explain the notation here. We start from here. A bad hypothesis is a hypothesis that will lead to a bad sample is a sample that will lead to a hypothesis with big error. Now, what do we have here? We have some unknown distribution D that generates points, generate papayas. We picked m of them independently. So the distribution over m tuples, over samples, is the m's power of D. We use D to pick the first one, we use D to pick the second papaya, we use D to pick the next papaya, and so on. And under this m power of D, we are looking at the sum. We only care about which papayas we picked. The label of the papaya is already determined by f. So by s restricted to x, I just means if s is x1, y1, up to xm, ym, by s restricted to x, I just mean x1 up to xm. My distribution doesn't pick y randomly. It picks the x's randomly, and the y's are defined by f. The labels are defined by my unknown f. So I want to upper bound the probability of picking a bad or a non-representative sample. Okay? So in order, or are there questions about this? I mean, what I'm claiming is if we will be able to show that the probability of this event is small, we are done. This is the probability that we'll pick a confusing sample. If it's small, then we are with high probability making conclusions that have errors smaller than epsilon. Any questions at this point? Yes. Oh, I'm just, yeah. I usually just use for probability of some event, I use this square bracket. It's the probability of this set. Okay? So I use D of A to denote the probability of hitting the set A. And my set A here is the set of all bad samples. Okay? Any other? Yes. Oh, you're just stretching. Okay. Okay. Now we want to analyze this set. So to analyze this set, we will introduce two more sets. So we introduce HB, which is a set of all bad hypotheses. So HB is going to be the set of all H in H, such that the true loss of this H is greater than epsilon. So this is the set of all hypotheses that if this is what I output, I failed. This is the set of hypotheses that I want to avoid. Okay? Now, I want to describe when will a sample lead me to a wrong conclusion. So I'm saying the set of misleading samples, a misleading sample is the set of samples is the set of samples that may lead to an outcome in HB. If I want to write it formally, so M is the set of all S restricted to X, such that, now how can I be, I'm using ERM. I'm using ERM over H. How can I be led to a bad hypothesis if there exists some hypothesis which is bad, but what is my empirical error on this hypothesis? When will I be led to a bad hypothesis in terms of my empirical error on this hypothesis? Yes?
When it's lower than all the other hypotheses.
When it's lower than on the other hypothesis, right? And lower here, I can say it's 0. So it's a set of all samples such that there exists a bad H such that the empirical loss of HB, of this bad H, is 0. OK, so this is something I want you to understand. What is a misleading sample? A misleading sample is a sample for which there is a risk that you will output a bad hypothesis. But you will output this hypothesis only if this hypothesis makes small error on the sample, 0 error on the sample. So the question is, could it be the case that you have a hypothesis which is really bad and makes small error on the sample? And we saw such hypothesis. The hypothesis that said that assume that I saw these points, and these 4 points was labeled testy, and this point was labeled testy. And I took the hypothesis to just say, just pick these two as tasty and everything else as untasty, right? So this hypothesis, the ERM that we saw before was really given as a hypothesis that had 0 error on the sample, but could have a big error outside the sample. But now it's not ERM in general, but it's ERM H. So a hypothesis is a sample is misleading if there could be a bad hypothesis that looks good on this sample. Yes?
Why is that the error of this H is less than the error of other H's can imply that the error of this H is 0?
Oh, because there is, we assumed, you see, our class H is the class of all rectangles. And we assume that the labeling is by some f, which is a rectangle. So in my class H, there is always the true f that makes 0 error. There is always a candidate that makes 0 error. When will you get confused? If there are also bad candidates that have the same error. So you don't know which is the good one and which is the bad one. Because remember, we are doing empirical risk minimization over H. Or we see a sample S. We want to pick someone with minimum error with respect to S. The true F is such a guy. The true F has 0 error. So if I'm going to pick someone else, this someone has to compete with the true F, so it must have also 0 error. Okay? I already have someone that makes 0 error on the sample. So if ERM is going to pick someone else, this someone else also must have 0 error on the sample. The question is, could I have a bad one that still have 0 error on the sample? The good one will always have a 0 error on the sample. Okay? Yes? Under this assumption of the theorem, we assume that H in general is finite. And since HB is a subset of H, it will also be finite. We will later extend it to the case of infinite H's. But here we assume that everything is finite. So what? No, it's not a set of all rectangles. The theorem says if capital H is finite, then we will show it. In the next class, we will show that it also holds for all rectangles. But for now, we only assume that it's finite. Okay? Right. So it could be the set of all rectangles, because now I'm assuming that H is finite. You can think of it as all rectangles whose coordinates are discretized to some discrete values. Okay? So now the next thing I want to claim is that the set of bad S's that I want to upper bound is a subset of this. Right? So we wanted to upper bound the probability that we will find an S that leads to a big error. When S will lead to a bad error, only if S is here. So I'm claiming that the set of all S such that LDF of HS is greater than epsilon, the set that I'm really afraid of is a subset of M. So now I have a question for those of you who still follow. Why is it not all of M? So let us recall what is each of them and why are they different. This is all the S's that will lead my learner to output a bad hypothesis. This is the hypothesis my learner will output. So these are all the samples such that the output of my learner is going to be bad. And these are all the samples for which there exists a bad hypothesis that looks perfect on the sample. So why are they not the same? Yes?
Just because there exists a bad hypothesis doesn't mean that it will be
Exactly. Exactly. This means there exists a bad hypothesis. This is the hypothesis that I selected. If I selected a bad hypothesis, of course there existed a bad hypothesis. But there could be cases in which there existed a bad hypothesis and didn't select it. Therefore, this set, the set of cases in which I select a bad hypothesis, is a subset of the set of all S's for which there exists a bad hypothesis. Maybe there existed one, but we were lucky and didn't pick it up. OK? So we wanted to upper bound the probability of this set. Since this set is included in M, it suffices to show that the probability of hitting S in M is small. So my conclusion is it therefore suffices to upper bound the M of the set of misleading hypotheses. Because if this set has a small probability, this is a subset. It will have an even smaller probability. And this is what we are worried about. OK, well, now I can rewrite this set. This is the set of all S's for which there exists a bad H. So I can rewrite it. So this will be bounded by the same as the dm of the union over all H in H bed of the set of all S such that LS of H is 0. OK, so that's my next step. Again, maybe I should use the square brackets. What I'm saying is that the set of all S's for which there exists a bad hypothesis is the union of all bad hypotheses of the probability that I will pick this. So let's draw a picture. If I pick a specific H, which is bad, then what I have here are all the samples, all S's. So if I pick some H, which is bad, there is only a small set of H's, of S's, that is going to lead. So this is the set of all S's such that L S of H is bigger than epsilon. This is the set of all samples, is 0. This is the set of all samples that may lead me to pick H. I will pick H only if it makes 0 error. For a single H, this is the set. And for another H, this is going to be the set. And for another H, this is going to be the set. For every hypothesis H, I have the set of all samples that will lead me to think that on which this looks perfect. Now, the bad case is that if I am in the set of samples that lead to a bad hypothesis. So it's the union over all H's which are bad of this bad case. So what we are doing now is also a very, very standard trick in probability. If you want to upper bound an event which is there exists an H something, it's the same as taking the union set of all of those events for particular H. There exists an H such that something bad happens is like the union of the bad causes of all those H's. Yes? M is a set of M tuples of Xi's. M is a set of samples. A sample is of size M. So it's a set of M tuples. It's all the M tuples such that if you saw this M tuple, there exists a bed H that looks perfect. Okay? And I say it's the union of all bed H's of the set that make this bed H perfect, look perfect. Now we are almost done. Now we just need, now we just need another two very basic tools from probability theory. So we need two basic probability rules. One is called the union bound. What is the union bound? Is that for any two events A, B, the probability and any probability distribution P of A union B is at most P of A plus P of B. I'm sure you have seen this before, the union bound. The probability of hitting a union of sets is at most the sum of the probability of hitting each of those sets. Okay? So that's the union bound, and why it is going to be relevant? Because we have a union here. And we want to bound it by the probability of each of those events. The other rule, which I'm also sure that you have seen, and these two rules are basically everything that I will need from your background in probability. So, is the rule of independence. If I have two independent events, what do I know about the probability of both of them happening? So, 2, if A and B are independent events, then the probability of seeing A and B equals what? If I have two independent events, yes? What? I don't hear you. What? Yeah, P of A times P of B. Okay? So these are the two basic rules from probability that we are going to need. So now we go back to here. Now we say that what we want to upper bound is the probability of this union. So it's enough to upper bound the probability of one of those, of each of those elements. And then take the sum because of the union bound. So now we are back to our proof. You fix for any fixed H in HB. Let us upper bound what we have here, the probability of this event. The probability, or the dm, the probability of the set of all samples of size m such that LS of H is 0. Okay, so let us see what is happening here. This is the set. This is my set of all x's. And I have some, think of it, this is the set of all my papayas. And I have some h, and this h is bad. So I can view, what does it mean that h is bad? If I have some h, and I can divide the space x into here, h is correct, and here h is wrong. So I have my space of papayas. I have some hypotheses. I divide my papayas into those on which H predicts correctly and on those for which H is wrong. Or in other words, H is wrong is the set of all points on which H of x is different than f of x. What do I know if H belongs to H bad? What do I know about this set? What do I know about the set of points on which H is wrong? I know something about its size. Yes? Its probability is at least epsilon. So the probability of this set, if H is an HB, the probability of having it wrong is at least epsilon. In other words, now what will happen, I take a sample, and on the sample, H is always right. So I'm saying that the probability of the set of all samples on which I don't make any error equals the probability of the set of all samples such that what happens? H of x1 equals f of x1 and H of x2 equals f of x2 all the way up to H of xm equals f of xm. So what am I saying here? I'm saying I will make zero error on H if for each element of my sample H coincides with the true labeling. But what is the probability that I'll pick a point on which this happens? What is the probability that I'll pick a point on which H and F agree? This probability is at most, so this is at most 1 minus epsilon to the power m. Okay, so here I made a small jump, and I'll explain this jump. You see, I have here events. x1 is such that H and F agree on x1. h2 is such that H and F agree on x2. xm is such that H and F agree on xm. These are m different events, and all of them are independent. Why are they independent? I'm picking the first point. I'm picking a random point. It could either fall in the area where H is right, or it can fall in the area where H is wrong. The probability to fall in the area where H is right is at most 1 minus epsilon, because I know that the wrong area is at least epsilon. So I pick a first point. The probability it will fall here is 1 minus epsilon. Then I pick the second point. The probability the second point will be such that H is right is also at most 1 minus epsilon. Why am I allowed to take the product of those events, of those probabilities? Yes? Because I assume that the different xi's are independently picked. So since they are independently picked, the event I am right on x1 and the event I'm right on x2 are independent. So the probability of both of them happening is the product of the probabilities. And I have m such event. If I made no mistake on H, it means I was right on the first point, and I was right on the second point, and I was right on the mth point. So the probability that this will happen is at most 1 minus epsilon to the power m, based on the independence of the x's. So now we are done with the proof. That was the difficult part. Why are we done with the proof? Because now I can say, now I can bound what I need. I'm using my union bound. I'm using my bound on this. So let's go back here. We wanted to bound the probability of having a bad S. We said that this is at most the probability of the set of M, of misleading S's, which is the probability of the union over all H in HB of the event LS of H, the set of all equals 0. Now, for this union, I use a union bound. So it's at most the sum of them all. So it's the size of HB times the probability of this event. And the probability of this event is at most 1 minus epsilon to the m. And this is at most the size of H times 1 minus epsilon to the m. So here I had a union over all H's in HB. I turned the union into sum of probabilities. So I have HB many elements to add. Each such element has probability at most 1 minus epsilon to the m. So I get this upper bound. I get this upper bound on the probability of my ERMH outputting a bad hypothesis. And this upper bound, as you see, it goes to 0 when the sample size goes to infinity. With large enough samples, the probability of making a bad decision goes to 0. Because this H was finite, and a bad decision is that it has error of more than epsilon. So the probability of picking a bad H goes to 0 as the sample size grows. So what we proved is that if we use ERMH on a finite class H, and if we assume that the correct labeling comes from the class, which is a strong assumption, then this strategy ERMH has very small probability of failure. Probability of failure that goes to 0 with the sample size. So next time, we will put it in a more general framework and extend it further. But this class was a good warning as to how terrible this course will become. This course is going to be a mixture of nice stories and horrible mathematics, and this is as horrible as it gets.